The objective of this lesson is to decompose volume into layers in order to find the volume of a rectangular prism. In the previous lesson, we discussed volume as an attribute of rectangular prisms. We practiced using the packing method to determine volume. In this lesson, we will learn how to decompose rectangular prisms into sections to allow us to calculate volume as a repeated addition expression. Let's begin with an image of an irregular area model. To calculate the area, we could decompose the shape into two rectangular sections using the information we have to determine the information we do not have. If we were to create a three-dimensional model of this flat image, it might look something like this. As a three-dimensional shape, we will calculate its volume, not its area. To calculate the volume of this new shape, we could count the number of cubes used in creating the shape, but that would take time and become increasingly inefficient with larger or more complex shapes. Instead, we can deconstruct the three-dimensional shape into smaller, more easily calculated rectangular prisms. In this way, we could create 2 or 3 separate rectangular prisms similar to the way we would have created 2 rectangular sections as we partitioned the irregular area model. If we were to write addition expressions to represent these decomposed shapes, the first expression would be 6 cubic units added to 12 cubic units, while the second expression would be 6 cubic units added to 6 cubic units added to 6 cubic units. Another way we could decompose the original three-dimensional shape would be to look for layers. We can better understand the idea of layers by envisioning a skyscraper. Each floor in a tall building is one layer. Riding an elevator from the main floor to the top floor, the elevator display counts off each layer as it is passed. Just as a building has floors, we can identify 3 distinct layers in our three-dimensional shape. If we were to decompose it along its layers, it would look like this. 3 layers of 6 cubic units each, or 6 cubic units added to 6 cubic units added to 6 cubic units. Notice that the expressions for the second and third examples of decomposition are the same, even though the shape was partitioned differently. If we take a moment to return to the irregular model of area, we will notice that each measurement is made in feet. When determining area given in feet, we calculate it using feet as our unit of measure. Rather than referring to our measurement of volume as cubic units, we can substitute the unit of measure in place for the word units. For example, each of our cubic units measures 1 centimeter on each edge. We call it a centimeter cube and can use it to measure volume in cubic centimeters. If we were to change our final addition expression to represent cubic centimeters of measure, it would become 6 cubic centimeters added to 6 cubic centimeters added to 6 cubic centimeters. The volume of the three-dimensional shape measured in cubic centimeters is 18 cubic centimeters. For further practice, students will determine the base of a rectangular prism, then note the number of layers. They will write the repeated addition equation that shows the volume of the prism. The objective for this lesson was to decompose volume into layers in order to find the volume of a rectangular prism. We met this objective by applying our experience with decomposing irregular area models to help decompose three-dimensional models of volume. We also identified a unit of measure and provided a measurement of volume using that unit.